Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 3 of the lecture on flood frequency guidance, Bulletins 17B and 17C. In our outline, we're at historical information. Now, this is the second half of the slide that we saw earlier on high and low outliers. Bulletin 17B's Grubbs-Beck test defined a high outlier threshold as well as the low outlier threshold. So systematic events above the high outlier threshold were designated high outliers. Those values weren't censored as the low outliers were. Those highest values are the most important parts of the data set in terms of determining the upper end of the annual peak flow frequency curve. So what the guidance suggested was seeking historical information, and primarily, it was trying to determine if that largest gauge event was actually the largest in a longer period of time than the length of the gauge record would indicate. Determine if it actually had a longer return period. If there's an historical period in which we know that that flood magnitude wasn't exceeded. And so in that case, 17B used something called the weighted moments algorithm, and Bulletin 17C instead uses intervals to define the unobserved years, the historical years for which we know that the large systematic flow wasn't exceeded. Right, so here's a few definitions. Historical information refers to information from human record keeping, and paleo information is instead talking about physical evidence from the watershed. Now, some of the paleo information is hundreds or thousands of years old, but it can actually be recent information as well, high water marks or tree scars from a recent event. Okay, more definitions. The systematic record is years in which stream flow is gauged or measured in some other way, perhaps reservoir inflows. The historical period includes years that weren't gauged, but for which some information is known. And so some examples of historical information: a large flow happened and can be estimated, that there were flows that exceeded some threshold, that there were no flows that exceeded some threshold. That's useful information as well, knowing that flows were lower than a particular value for some additional years. Right, so an example is the 1997 flood event on the American River was known to not have been exceeded since 1862, which is well before the gauge record began. Right, so here's an example of some historical information. This is a newspaper article from 1907 in Wheeling, Ohio, and it describes not just the flood event that happened that year, but it also mentions an earlier flood event in 1884. These are some post-flood reports that Mike Bartles pulled together. These have descriptions not just of the floods noted in the report, but sometimes also have information about earlier historical events. This is an example from Germany that has mostly some more recent floods, but one as far back as the year 651. Here's another that would be called historical information from the Potomac River. This flood post is actually more than just information, it's actually public awareness of flooding, right? If you're in the Great Falls Park and you see this flood post and see that there have been times when water reached this high over your head, it would certainly raise your awareness of the instance of flood events. Right, and this in the lower right is an example of paleo information. These trees are called schooners, and what happened here was water was high enough to inundate the trees and tip them sideways, but the trees didn't die, and this one sent up another limb to grow vertically. So you get two pieces of information here. You have a low threshold that we know the flood event exceeded, and you can also get a date, right? By coring the tree and counting rings, you can see when this additional limb started to grow. This slide shows a few more examples of paleo flood information. We have a tree scar, we have a slack water deposit. So when water gets above a certain level and drops out deposits, that's evidence that water got that high. We have an erosion scar to show that flow got to this level. And we also have some information about flow not having gotten as high as this area here on the right. So this is sediments that would have been scoured if the water had gotten this high. So this is something that can be called a non-exceedance bound because water didn't get this high. And we can date the period in which water didn't get that high based on what is currently there. So here's some more definition. So we have an example of a period of systematic flood events, and then we have an historical period that has four exceedances of some threshold. The way Bulletin 17B would have handled this historical period would be to note the historical floods, but then assume that for the other years in the historical record that weren't observed, that the moments were similar to the systematic period. Right, so it would assume that the systematic period was kind of stretched across the historical period. And the way that was done was to give higher weights to the systematic years within the computation of the moments. And so their influence would stretch across the historical period. And then the historical events would have each a weight of 1. Right? This was called the weighted moments algorithm. The way 17b handles the same situation is that each of the unobserved years is replaced with an interval from 0 up to the known threshold. So here's an example from Virginia on the Meherrin River. So we have 60 years of annual peak flows. To fit a log Pearson type 3 distribution to just these values gives the pink curve. But the USGS actually records quite a lot of information for these sites. So before USGS posted the annual peak flow data on the web for us to download, they published a book every year that had a page for each site. And they published flows, not just the annual peak flows, but also lower flows from each year that would be helpful in doing a partial duration analysis, and also with a lot of historical information recorded. So here we see in green, the flood event of 1940 was the greatest since 1873. So here's that 1940 event down here. It was before the beginning of the gauge record and was estimated to be 40,000 CFS with a gauge height of 30 feet. And here in red, there's several historical years where there's either an estimated stage or some description of what the stage might have been with respect to other years. Right, so let's bring in this information one piece at a time to see how it affects the curve. So let's start with the 1940 flood of 40,000 CFS, right? So if this was our gauge record, we now have an additional event in 1940 at 40,000 CFS. So if we were to plot that on our frequency axis, it would plot here at about a 1 in 70 event, because that makes this a 70-year record. And the other events have been pushed a little bit to the left as the dark blue values, right? Their plotting positions have changed a little bit. And fitting a frequency curve to this data with this return period would raise the frequency curve on top. But next we can bring in the information that that 1940 flow was known to be the largest since 1873, right? So we've increased the length of record all the way back to 1873. And we know that for this period of time, the flows were less. In fact, in the Bulletin 17B approach, we'd assume that the moments were similar to what was observed in the systematic record, right? But how this is going to look on our frequency plot is this 1940 event that had plotted as 1 in 70 is going to move over and be plotted as only 1 in 138. And of course, the plotting positions aren't going to affect the fitted frequency curve, but they show us how the curve is going to be influenced with the fit of the log Pearson 3 distribution. Right, so the effect on the fitted log Pearson type 3 distribution is to make it a little bit lower at the upper end. All right, finally, we have this information about stages in several historical years. They don't give flow estimates, but I decided to make this a more interesting example to do a little bit of estimation. So I plotted flow versus stage from that table from 1951 to 1958, and then also brought in the estimate of 40,000 CFS for a stage of 30 feet. Right, this is just a polynomial fit to this data, and I brought in the stages that were noted in the table to get flows, and the table also notes the years in which they occurred. So we've now extended our information to include these 6 historical floods. So if this was a Bulletin 17B, we'd have to be a little bit careful about which of these historical events we brought in. And in fact, the high outlier threshold was by definition set to the lowest historical event. And that would have then designated all of these values over 15,000 CFS as high outliers as well. We'd have had to go in and override that high outlier threshold to do something more sensible. But for a 17C analysis, this information is a little bit easier to use. This early event at 15,000 CFS would have allowed us to define a perception threshold that said we know all of these unobserved years were actually lower than 15,000 CFS because we know we would have perceived everything above 15,000 CFS, right? So to bring all of these events in a Bulletin 17C, expected moments algorithm fit would give us the red dots showing the historical events and the light blue line for the expected moments algorithm fit. Right, so it's allowed us to bring in quite a lot more information. So what assumptions are we making by including historical or paleo flood information? Well, what we were calling the homogeneous or identically distributed assumption can also be called stationarity since we're collecting our data across time. So we are assuming that those events are part of the same population as the recent events and that the watershed is not changing across the period of time that we're looking at, either in development or in the outcome on the hydrology and the hydraulics. Right, we're also assuming consistency, defined just that the estimates of historical flows are equivalent to the systematic gauge measurements. That's something we can address more easily in Bulletin 17C because we have the ability to put intervals on the historical flows if we don't believe that they were measured as accurately as gauged flows. Right, the stationarity assumption, though, is one that we still would be making, and we have to consider whether it's a safe assumption to make. Right. So a quick summary of how we use historical information in Bulletin 17B and in 17C. So 17B could use two types of information. It could use historical events that had estimated values, though not exceedance or non-exceedance information. And it could also bring in unobserved historical years that are known to be lower than some high outlier from the systematic record. So Bulletin 17C can use quite a bit more information. It could use an interval for the historical event that might have quite a bit of uncertainty in its estimation, and can also use intervals for all of the unobserved years in between the historical events and the systematic record. And then the other type of information that the expected moments algorithm could use is the knowledge that flows in certain years were either above or below some threshold. Either we know an event occurred that exceeded some minimum level, or we know that for a certain period of time, no flows occurred that were above some threshold, and therefore flow must have been below. Okay, so that is the end of the third video on historical information. And next we're going to move on to the last three topics. So I will see you in video 4.